So today we want to talk about how to graph secant and cosecant. So to start with, on our note sheet here, we have this table. Now for the sine values, we should know these, right? The sine of 0 is 0. Pi over 2 is 1. The sine of pi is 0. 3 pi over 2 is -1. And 2 pi is 0. Okay? Now, this cosecant is just the reciprocal. So now we know the reciprocal of 1 is just 1. And we know the reciprocal of -1 is just -1, right? The sign stays the same, you just flip it. But if you probably want to think of 0 as like 0 over 1, or 0 over some non-zero number. When you take its reciprocal, you divide by 0, which we can't do. So this would be undefined, and this would be undefined, and this would be undefined, okay? Everywhere our function, whether it's the cosecant or the secant, or next time we're together, we're probably going to talk about tangent. Anytime you get undefined, it means there's going to be a vertical asymptote. Okay? If you remember when we first defined trig functions, we defined their domains, and it was like this. You had all these repeated not equal to's, like it could not be pi times k or things like that. That's everywhere that domain fails to exist, or everywhere the output fails to exist, all those x values are going to have vertical asymptotes. So these are not going to be nice smooth graphs like our sine or cosine. They're going to have a bunch of vertical asymptotes. See, cosine values, we have 1, 0, -1, 0, 1. Right? And then we take the reciprocals. Reciprocal of 1 is 1. Undefined, -1, undefined, 1. We good? Okay, so we're actually, to graph, we're going to actually look at the sine and cosine and just remember this reciprocal property, right? Where these things happen, we're still going to we're going to evaluate our function at these same points that we're used to, right? We're going to define our period as being 2 pi over b, just like we have with sine and cosines. But we just need to know that the zeros become vertical asymptotes, the ones stay ones, the negative ones stay negative ones. Okay, so the first thing we want to graph is just the parent function for cosecant functions. Okay? There's different ways to do this, but the way I'm going to show you is first we're going to make a table I'm going to have an x column, and then I'm going to do the sine of x, and then I'm going to have another column for the cosecant of x. Okay? We're going to actually just take advantage of the fact that we have these reciprocals. Now, if it was the cosecant of 2x, we would make this the sine of 2x, right? Or if it was 3 times the cosecant of x, we'd make this 3 times the sine of x. Does that follow? Like we're just replacing the cosecant with sine. So then we know that from this, there's no multiple on x, so the period would be 2 pi. So we get the same values that we're used to seeing, correct? Okay. And then we know the sine of 0 is 0, 1, 0, -1, 0. So then our cosecant will be undefined, 1, undefined, -1, undefined. Let's see what that's going to look like as a graph. Right? That's kind of the important thing here. So kind of the same ideas is that we'll show, label our first period on the x-axis, label the y-axis. So pi over 2, pi, 3 pi over 2, 2 pi. So what's going to happen here, the first thing we'll do is everywhere that the cosecant is undefined, as I said before, will be a vertical asymptote. So we're going to get a vertical asymptote at 2 pi. Again, we just make that as a dashed line, just like we did with rational functions. Okay, so we have those, and then we'll go ahead and plot our points. Okay, so we'll go ahead and plot a point at pi over 2, 1. And at 3 pi over 2, -1. So this is going to be enough of the graph. This is going to show one full period. When we're graphing with asymptotes, you want to make sure that your edges are asymptotes. Like you don't want to just stop right in the middle. But now what happens here is we know if we think back to our sine values, we know they are always between -1 and 1, correct? If you evaluate a sine function. Well, if you take the reciprocal of 1, we saw that you get 1, but if you take the reciprocal of 1/2, you get 2, right? Or if you take the reciprocal of 1/3, you get 3, or any of those. So what's going to happen is this will have no points between -1 and 1. So what you do is you get these, and it's just going to be, I always think of it as kind of turns of the inside out. So it just has these pieces here, right? This would be, this point here at pi over 2, 1 would be a minimum for this branch of it. Here at 3 pi over 2 -1, that would be a maximum for that branch. And it's just going to keep repeating, right, if we wanted to, because this is one period, it started to repeat its behavior. So if you wanted to put some more values over here, right, we're at the edge of the period, we go over 1, we're here, go over 1 more, we have a vertical asymptote, go over 1, we're down at -1, go over 1 more, we have a vertical asymptote, right? So this would be 2 periods now. Now, if we were asked what the domain and range were for this, which is definitely something you're probably going to be asked here. Our domain, well, we see that pi doesn't work, and 2 pi doesn't work, and 0 doesn't work, and this would be 3 pi and 4 pi. So the way we tend to write that is we say x cannot equal k times pi, where k is contained in the set of integers. Remember, we use that little z looking thing with the number line. This means the set of integers, which would be our numbers, our positive and negative whole numbers, right? So like -3, -4, etc. Right? On up. And then our range here, if you think about compressing this onto the y-axis, we'd have a point at 1, we'd have everything above it, correct? And then we'd have a point at -1 and everything below it. So our range would be that y is contained, if you want to put that symbol there, you can, from -infinity to -1 with a bracket, because -1 is included, union 1 to infinity is how we would write the range for that function. Does that seem reasonable, everybody? Yeah. Okay, let's go ahead and look at what the secant of x would look like. Maybe go ahead and start that. That's the second one on your worksheet, and we'll take a look at that. And just real quick before we go on to the next one, as we look at this, if you don't put this on your graph necessarily, but it's good to know, is here, if you think about what the sine values were, notice that you had a 0, a 1, a 0. So if you notice that the sine values kind of complete that, just fill in the middle part, correct? So that's really where I think of it as like you're turning it inside out, like you're, that might be helpful, right? Because wherever you have a maximum here on this part of the sine curve is where you're going to have a minimum there on the secant curve. So that's just something to kind of consider. Again, it would not be good to graph it every time like that, but it is something good to kind of make a note of that there is a relationship there. Okay, so next let's look at the secant of x. So we're going to repeat this process here, but again, we know the secant is the reciprocal of cosine. That's going to give us 1, 0, -1, 0, 1. Okay. So, because again, these are the peaks, right? This is the valley. This is where it hits 0. So for this, for our secant, we're going to get 1, undefined, -1, undefined, 1. This will be a little bit more work because we want our graph to have an endpoint or a vertical asymptote on the left edge and a vertical asymptote on the right edge. You really don't want to stop right in the middle of a piece. I think it's better to just go from one to the other. There's 1, there's -1. So pi over 2, pi, 3 pi over 2, 2 pi. Again, just need to label the ones that we have, but then we'll want some more. So as we look here, 0, 1 is up here. Pi over 2 undefined would be a vertical asymptote. And then pi negative 1. And then a vertical asymptote. And then 2 pi 1. And again, we don't want to just stop here. So this is one period apart. So if we go to the right, we see a vertical asymptote. Now if you wanted to, actually this graph, you have an upper part and a lower part. That does show us a complete period, but I still probably go over one more. So here are the ends. See that both at those, and we go left is a vertical asymptote. So that's actually 1.5 periods. Does that make sense there? Right, this and this together make up 1 period, or this and this together make up 1 period, or all together it's 1 and 1/2 periods. Okay. We good? Yep. Okay, so let's talk about the domain and range of this function, just to make sure we can write that out. So for the domain, what you'll see here is that we're undefined at pi over 2 and 3 pi over 2, and that would be 5 pi over 2, and that would be negative pi over 2. So what you can do when you have these repeated discontinuities, right, vertical asymptotes, we're still going to say x is not equal to, just pick one to start at. So pick pi over 2, it's probably the one most people would pick, and then look at how far apart they are. They're pi apart, aren't they? So we'd say plus k pi, where k is contained in the set of integers. That's that z symbol again, which didn't do a very good job. I think it's short for Zahlen, which is the German for 2 count, I believe. And then the range here would be y goes from negative infinity to negative 1, union 1 to infinity. Right? So it's actually, the range there is the, I guess, the complement of the range of the cosine curve, right? It went from negative 1 to 1. This goes everywhere except between negative 1 and 1. So let's look at, now we'll look at a 1 or more here where we actually have some different things done to it, right? There's a number out in front, or the period changes, or we have a phase shift. All those things that we did before with sine and cosine graphs. Let's go ahead and look at an example here. We have y equals 1/2 cosecant 2 times x plus pi over 4. We're going to use the same technique we did before. We're going to look at the table we make for sine, the reciprocal of cosecant, and use that to produce the significant values that we need for the cosecant graph. Okay, so if we think about the function, who can even make it? Well, let's think. If we think about the function y equals 1/2 sine of 2x plus pi over 4. Again, I always like to put that bracket there, but didn't have it to start with. But for this, the first thing we'd want to do is figure out the phase shift, right, which is negative pi over 4. And then the period would be 2 pi divided by pi, or 2. So that would just be pi. So what I'm going to do here is, to make my table, I'm just going to kind of do it like the sine version and then the cosecant version. We could write it all out if you wanted to, but it's not a huge deal there. So with this, we're going to start at our phase shift, so negative pi over 4. Right? When we add pi to that, we're going to get 3 pi over 4. So if you would, take a minute and let's fill out this first and second column here. We should be able to do that. Okay, so as we look at this, when we average negative pi over 4 and 3 pi over 4, that's going to give us pi over 4, and then 0, and then pi over 2, right? It's just as we did with just graphing a sine function. Now, to graph this sine function, hopefully by now you realize that if you build your table correctly, it's always 0, 1, 0, negative 1, 0. Right? I know that a lot of you have seen that. And then the amplitude is 1/2, so this is going to be, let's see, so 0, 1/2, 0, negative 1/2, 0. Okay. Now, the values, like here it was okay because we still had a sign with 0, so we know that reciprocal there is. Here's where it gets a little confusing. We don't actually, the part that's the reciprocal is the 1 and the negative 1, correct? So for this is still going to be undefined. Wherever the sign itself was 0, we still get undefined. This is still going to be 1/2. It's not, you're not going to take the reciprocal of that. The reason being, if you put 0 in here for cosecant, you get the cosecant of pi over 2, which is 1, right? And then you do 1 times 1/2, which is still there. So really, wherever you had the zeros become undefined, everything else will stay the same. And if, as I showed you before, how you could kind of imagine that sine or cosine curve in the middle there, it's still going to come up and hit they're still going to share the same points. It's still going to be this function kind of inside out, right? Where the max on the sine function becomes the minimum of one part of a cosecant. So to graph this one, let's see. So nicely we have 0 there. So negative pi over 4, pi over 4, pi over 2, 3 pi over 4. And something I like to do too is if I have a vertical, I don't in this case, but a vertical asymptote on the y-axis, is I just extend it up above it and below it, but there's not one there. So we get here, here, here. We have 1/2, negative 1/2, so that's up here, and then down there. Again, so at this point, if you could even think of the sine curve, that where it hits the midline, that's going to give you your vertical asymptotes, right? Where it hits a peak or a valley, that's going to give you a point on the cosecant curve. So that graph, that's one period of that graph, right? You could just, if you need to pick more periods, you could do that. Are you doing okay there? Okay, the one thing, and we'll wrap this video up here, but then we'll get some more practice here. But the one thing to be kind of aware of is if we look at this function, suppose that it had a +3, right? So it has some vertical shift with it, correct? That'll change some things here because what will happen is all of these, the sine values, you'll add 3 to all of those, correct? So that would change this to 3.5, 3, 2.5, 3. Oh, sorry, I did that wrong. 3, 3.5. Oh, okay. I'm sorry, I'm confusing myself. 3, 3.5, 3, 2.5, 3. Notice that there's no zeros in there anymore, correct? But still, it's where that midline would hit. So at these 3's would still be undefined. And you could check that by when you plug in here, when you put negative pi over 4 in here, you get 2 times 0. We know the cosecant of 0 is undefined. So that's where the one kind of could be a little bit tricky here. I wouldn't think you'll probably see a whole lot like this. But what happens here is the whole thing just gets shifted up 3 units, correct? So our graph would look different. It would look like so let's do so we did it again. I keep forgetting that we have a phase shift on this graph, and I keep making mistakes. There we go. That's pi over 4, pi over 2, negative pi over 4, 3 pi 4. So there's our vertical asymptotes. But then those other points will be up here at, oh, did I do it wrong again? No, it's right. And then we have 0, 3.5, which would be here, right? And then pi over 4 undefined, 2.5 would be here. Right, so what this would look like. Would look like that. Now we still have this little band, right? Where if we think about the original sine, if we think about this sine function, it would sit right here in this band. That sort of thing. So just to kind of be aware. For both of these that we did, well, for this one that we're looking at, the domain would be x cannot equal. So in this case, pick any location of a vertical asymptote. Let's pick pi over 4. And then they seem to differ by pi over 2, don't they? From one asymptote to the next. So you'd say plus pi over 2 times k, where k is contained in the set of integers. The range here would be y is contained from negative infinity to 2.5, union 3.5 to infinity. So just, are we doing okay with how these are graphed? Yes.
Would you ever see it in?
All right, so just here, if you notice, this, I went ahead and did, this dashed horizontal line here is just the midline, which was at 3. So another way to think about this is, if this would be our sine, 1/2 sine of 2, x plus pi over 4 would be right here. And if you look, wherever there was a peak on the sine is the bottom of a curve of the cosecant. Right? Wherever it hit the midline on the sine is where you have a vertical asymptote. Wherever you have a trough or a valley on the sine curve, you have a piece that opens down. Yes?
So when you make the sine cosecant table for the equation before this for the regular one, sine was 0 and then you make cosecant undefined because I get it, it's the reciprocal. But then you put sine as 1/2 and then the cosecant was also 1/2. Shouldn't it be the reciprocal?
No. The question is when we did the last one here, we had, I think we had, so back to here, right? Was we had, let's see, 0, 1/2, 0, negative 1/2, 0. The question is shouldn't these become a 2 and a negative 2? Which is a completely reasonable question, but the answer is no. Because what happens is this multiplying by 1/2 happens after the cosecant's evaluated. Because when you evaluate the sine is when you're going to get the zeros and the ones and the negative ones. Then you're going to take the reciprocal. So the reciprocal of 1 is still 1. Then you multiply by 1/2. Is why that. So that's kind of tricky. That's maybe where this idea here of thinking of the sine or the cosecant, or I'm sorry, the sine or the cosine curve, and kind of flipping it inside out might be helpful. Because this would have an amplitude of 1/2, right? And that these were also going to be 1/2. So yeah, that's kind of something you have to be careful about if you do it this way. But it beats having to actually plug things into a cosecant function because no one knows. I don't know my cosecant values very well. I just always use sine values. Would be the idea there. But if you needed to, you could, right? You could say, put 0 in here and you get 2 times pi over 4, which would be, what, the cosecant of pi over 2? And you think about, okay, sine of 2 is 1, reciprocal 1 is 1. So you got to do all that thinking. But that's why that is.